So if you remember from last week when Peter Rohde gave his talk on what the distant future of quantum communication looks like, he mentioned a couple of ideas about sending information around the world across quantum channels. And he had a picture of some satellites surrounding the Earth all sending information to each other, and that you could create a bunch of links, and together you could transfer quantum information all across the world. So what we're going to do in this lecture is take a look at how specifically that actually works, and just show with the basic circuits. It's a pretty simple setup. All you need is a bell pair, an entangled bell pair, and with that you can do all sorts of interesting stuff. And so we are going to talk about what's the point, why would we want to teleport quantum information, how we can do it, discuss a little bit about bell states and entanglement, and then discuss quantum teleportation. So the idea is we want to be able to send quantum information, and contrary to a lot of popular ideas on the subject, it's not about sending information faster than light. We're not going to be able to transmit a message across galaxies in the blink of an eye. There is an interaction that happens instantaneously and non-locally, but we're not going to be able to send information across the galaxy, Star Wars style. I don't even know if that's a thing in Star Wars. I have seen it though. Okay, so what if you were to try to teleport something using this bell pair? What could you try to do? Well, one way to do it would be to measure the quantum states that you're trying to send, and just send across the classical information of the measurements. That is, I mean, you could do that, but you would certainly lose some information. Remember that when we make a measurement, we're reducing the amount of information we have to just a classical bit. So that's not going to work. We could try to make a copy of the state and then put the qubit copy in a secure box and somehow send it somewhere on a truck halfway around the world. That's not going to work either, because it turns out, due to the no cloning theorem that Peter Rohde mentioned as well, you can't actually make a copy of a quantum state either. So why not just send the qubit through space? The main reason would be there's a bunch of noise, decoherence. It's tough to send qubits. They're very fragile. They require very low temperatures. And so we would unlikely to be able to retain the information by sending the qubit directly. So our only option here, or the most feasible option, is to do this teleportation. And so the key to how this process works is the entanglement of two qubits. And what we can do is we can set up two qubits in a bell state, and there are 4 bell states, but this is sort of the easiest one to think about. We have an equal superposition of the state 0, 0, and 1, 1. So this is a bell state. And what we're going to do is take these two qubits after we've entangled them, and we're going to separate them distance-wise. So we take these two qubits, we entangle them in some place, and then we send one to Europe and the other to China, and they're still entangled. Just because you move them doesn't mean they're not entangled anymore. And so the whole key to this is that we have a bunch of these bell pairs that have been separated in space. So just a little review of how entanglement works. We have this bell state here, 5+. It's a superposition of 0, 0, and 1, 1. And suppose we want to measure this state. We measure the first qubit, only the first qubit, and we obtain the outcome 0. What is the probability that we measure 0, what's the probability that we measure 1 for the second qubit afterwards? So we measure the first qubit, we get 0. What's likely going to happen with the second qubit? Yes, Jakob's got it right. With 100% probability, we're going to measure 0 on the second qubit. And what's really interesting about how this works is you could separate these qubits by 100 million miles, and as long as they're still entangled, if you measure the first one at the exact same moment and any time thereafter, even if there hasn't been some sort of light speed communication between them, it goes faster than that. It's instantly at the exact same time. The qubit far, far away will be affected by a measurement on one end. So that's cool. Let's try another one. Suppose we have a qubit in the Bell state, same as before, equal superposition of 0, 0, and 1, 1. What happens when we apply an X gate to this system? What's the new state of the system? We apply an X gate. You can leave out the 1 over square root of 2 if you're typing it. It's kind of a nuisance. Ooh. Yeah, okay, so the second exercise, we have a Bell state, and it's the same Bell state as before. It's an equal superposition of 0, 0, and 1, 1. What we're going to do is apply an X gate to the first qubit. So an X gate is the NOT gate, right? It's going to flip the bit, flip the first bit. What's the new state of the system? Okay, so we have 1, 0, 1, 1. Any other possibilities? Any other ideas? Oh, and you guys probably want to see me as I'm talking. Sorry about that. Hello. 1, 0, 1, 1. 1, 0, 0, 1. Okay. Seem to have a crowd mentality here. Okay, so people are going back and forth on this one. Let's do it out. Let's do it out. Let's go ahead and go to the Jamboard. So we have the state 0, 0 plus 1, 1. We're going to apply it to this whole state. And for now, I'm going to leave out the normalization factor, but know that there's a 1 over square root of 2 thing in front. So we're going to apply xi, meaning that on the first qubit, we're going to apply an X gate. On the second qubit, we're going to do nothing, which is the identity gate. Okay, so what we can do is apply this gate using the properties of linearity to each of the superposition branches separately. Okay, so xi on the first gate is 1, 0. 1, 0, because we flipped the first bit. So it was 0 and now it's 1. Okay, and then second bit, the second branch of the superposition, the first qubit is in the 1 state, and so we're going to flip it to the 0 state. So this is the new state of our system. Okay, this is the new state of our system. And we should have a 1 over square root of 2 factor in front of it. Okay. So everybody good on that? Are we clear on that, how that works? Okay, good. Good. And this is also a Bell state, by the way. This first Bell state is not the only one. There's also an entanglement happening here. For instance, if we were to measure the first qubit, and we got the 0 outcome, what is the likelihood, what are the measurement probabilities for the second qubit? You guys can put in the chats. That's right. Okay, so now, instead of the two measurements being correlated, they're, I don't know if anti-correlated is a word, you're certain to get the opposite measurement on both qubits. Okay, so if you measure 0, you're certain to get 1 on the other qubit, and if you measure 1, you're certain to get 0 on the other qubit. So this is its own form of entanglement, yeah. So let's return to our problem here, and this other entangled state is going to be important coming up. Okay, good. Great. So a little bit of a primer on how entanglement works, just because there's so much about using quantum teleportation to transport information faster than the speed of light. Einstein actually brought up the idea of an entangled pair in this, what he called spooky action at a distance, because he thought quantum entanglement was nonsense. And Knauf sort of hinted at this. A lot of people who were coming up with the ideas about quantum mechanics thought that it was ridiculous, and they didn't like their ideas. So this was Einstein's way, this spooky action at a distance, this was Einstein's way of saying, this is impossible. There's absolutely no way this could be true, because if it were true, then you would have this interaction that's happening between the two entangled qubits at a speed far faster than the speed of light, and that's impossible. And so it was this conundrum for a while, but recently people have done experiments, and it turns out this is exactly what happens. So you take two qubits and you separate them by a very large distance. And if you measure the first qubit, we know from the third axiom of quantum mechanics that the state is going to collapse. But what's interesting about this is instantaneously at that moment, the qubit that's really far away also collapses. And so you have this interaction that's non-local. It happens simultaneously. And so it does work this way. But as we'll see, this doesn't allow us to transmit information any faster than the speed of light. So, okay, so on to how this quantum teleportation is actually going to work. Any questions on the entanglement part so far? What we're doing here? Okay, great. So on to how this is going to work. As a setup, we have Alice and Bob. Oh, okay, we got a question. Yes. This is the whole idea behind quantum teleportation. We're going to explain how we can use this entangled pair to transport information. Yep. And so this is now the part where we explain how that works. Good question. Okay. So as a setup, you have, let's just say, Alice and Bob. The standard communications scheme involves two agents communicating with each other, and it's always Alice and Bob. So Alice has a qubit in the state psi, and she wants to send the state psi to Bob. Okay, wants to send the state psi to Bob. And the other thing that we need, and Peter Rode mentioned this in his talk, we need a currency. We need these entangled qubits. And so however much information we want to transfer, each qubit state psi requires its own pair of entangled qubits. Okay, so if we have a bunch of psis, we need a bunch of pairs of entangled qubits. So that's what we need. And we also, yeah, those are the only things. So there are 3 qubits total in the system. We have the state we want to send, which Alice has. Alice also has one of the Bell pair. and Bob has the other bell pair. So we've taken these two qubits, we've entangled them, and we've sent one to Alice, and we've sent one to Bob. Okay, so here's what's going to happen, just a quick overview. So Alice is going to entangle her qubit, this psi, the state she wants to send, with her bell pair. They're going to get entangled somehow. Okay, and we're also going to call this state psi the password qubit, because in security protocols, if we want to send something securely, quantum entanglement is a good way to do this. So we'll call psi the password qubit sometimes, and you'll see the notation later. Okay, so Alice is going to entangle her bell pair with the password qubit, and then Alice is going to measure both qubits that she has. So both the password qubit and her bell pair, her single qubit that she has of the bell pair. And in turn, we know from the third axiom of quantum mechanics that this is going to collapse the qubit that Bob has as well. And so Bob's qubit has been affected. So before Bob measures, though, what's going to happen is Alice is going to send her measurements to Bob. So Alice is going to measure before she measured these qubits, and she's going to send the classical results of those measurements to Bob. And you'll see why that's important later on. And then, based on Alice's measurement, Bob is going to apply some quantum gates so that he can recover the password state. Okay, so it's really cool how this all works. So here's an overview of how this works. Here's the circuit. So we're going to be talking about four different steps. The initial state we'll call psi 0. And that's going to be what's the state of the system right at the beginning before anything starts. And you can see we have our bell pair, and then we have our password qubit. Then Alice is going to entangle her qubits together, the two that Alice has, and then apply a Hadamard. And then we're going to have another state that we want to look at, and then Alice is going to measure, and then we're going to have another state to look at, and this is the one that Bob is going to affect, and then we're going to have finally psi as an output. Okay, so there are each of these stages that we want to take a look at. And so we'll keep track of where we are in the algorithm at each step. Okay, so step 0. We have the qubit we want to transport, the password qubit, and it's in the state alpha 0 plus beta 1. This is the general state of a qubit. So no matter what happens with psi, any psi we want to send, this is going to work. Okay, alpha could be 1, alpha could be 0, or anywhere in between. And of course, alpha squared plus beta squared equals 1. That's a precondition on the state of a qubit. Okay, so then we have also the bell pair, and we're going to label those qubits by A and B. The bell qubit that Alice has is A. The bell qubit that Bob has is B. And we're going to use blue to kind of color code the difference, because we're going to have a lot of branches to look at. So this system has 3 qubits, and remember, Alice has 2 qubits and Bob just has the 1. Okay, and you can see that this is the entangled state 0, 0 plus 1, 1. Where Alice's bell qubit has a equal position of 0 and 1, and it's entangled with Bob's qubit. Okay, so there we are. That's psi 0. That's where we are. Now, step 1. We're going to apply a C naught, and this is the description of C naught. Okay, so depending on the value of psi, we're going to do something to Alice's qubit, Alice's bell qubit. Okay, and so what happens is, if in the case that Alice's qubit is 0, and it could be any superposition, so there's going to be a superposition here, there's no action on the Bell state. There's no action on the Bell state. But in the case that there is, that in the case of 1, the control knot is going to do something, and it's going to flip the first qubit. So remember when we talked about applying a NOT gate to the first qubit in an entangled pair, and we achieve this state over here, this is exactly what's happening, right? So in the case that we did nothing, we just maintained our original Bell state. And in the case that of 1, that we did apply the NOT gate, you end up with this state. Is everyone clear on how this comes together? How the control NOT gate leads to this state? This is important, how we got there. Okay, good. So we have this state of 3 qubits put together. The 3 qubit state. Okay. And it's a superposition of the Bell state without the change and with the change. Without the, okay. So now we're at psi1. Yes.
Let me ask you a question. Go back to that last slide if you wouldn't mind. When Alice entangles her qubit with the password qubit, doesn't that, wouldn't that act as a measurement and collapse Bob's qubit?
That's a good question. So no, no. An entangling gate, the C0 is what we would call an entangling gate. And it's a unitary operation. It's a unitary operation on 2 qubits, but it's an equally valid quantum gate, and it will not force a measurement. So we have not collapsed any superpositions here. And this isn't the end. We're actually going to create more superpositions before all this is said and done. Right now we have 4 branches, if you will, and we're going to end up with 8. So nope, there's no collapsing yet, but when Alice measures, then you will get the collapsing that you're talking about. And now, since we've entangled the password qubit with Alice's qubit, now you'll notice that they're all entangled, because we know already from the start that A was entangled with B, but now that we've entangled the password qubit with A, P is also entangled with B. So they're all connected somehow. If we were to measure the password qubit, we would have some collapse that would affect the state of the B of Bob's Bell qubit as well. Okay, so now we're at psi1, and we're going to apply a Hadamard gate to the password qubit. Okay, and this is going to create a superposition, a further superposition on the password qubit. So how does the Hadamard work? Well, on the branch of the superposition for the password qubit that is 0, the 0 is going to be transferred to the plus state. The plus state is the Hadamard state, 1 over square root of 2, 0 plus 1. And you'll see we're using these P subscripts to denote the password qubit. Okay, and if the password qubit is 1, that's going to be transferred to the minus state, 0 minus 1. Okay, so you can see now what happens. The previous state, psi1, we applied the Hadamard to the password qubit, which is in red. So only right now the red is going to be affected by what's happening here. Okay. And the 0 state was transferred to the plus state, and the 1 state was transferred to the minus state. Okay, so we have alpha plus beta minus. And we can write out more in more detail exactly what's happening here. This is an expansion of what's going on. We have alpha 0 plus 1, and then beta is 0 plus 1. Okay, so now we've created more branches. We're expanding our superposition. Okay, and I can rewrite this by distributing these states. So I can say we have 0 password qubit times 0, 0 for both Bell qubits. I could have 0 times the 1, 1. I could have 1 times the 0, 0, and 1 times the 1, 1. And that's 4 terms just for the first term of this equation. Okay, and I really should, oh geez, now, these equations are a nightmare. Ah, this is better. Now you should be able to see the whole thing. Okay, so now it should collapse. You should be able to see now what we've done is distribute each of these layers. So now that we have a superposition of 8 terms. Okay, we have alpha over 2 times all 4 of these combinations plus beta over 2 times all 4 of these combinations. Is it clear how this comes about? Because this is probably the hairiest operation of it all. Let me know if you want me to explain it again. Not really. Okay. Where did the negative go in the second half of the last equation? That's an excellent point. There should be. There absolutely should be. There are negative signs dispersed somewhere. I will have to fix this. It appears more correctly later on. Yes, okay. Sorry about that. Yes, so this should be a minus, and then fixing it now would be a massive, it would be hard because all the colors makes the equation different. But yes, there are minus signs that dispersed here. But what you can take away from this, other than the missing minus signs that should be all over the place, is that we now have 8 equal superpositions. Not necessarily equal, but we have 8 different terms. And that corresponds to the 8 basis states for 3 qubits, 1, 0, 0, 0, 0, 0, 0, 1, 1, 0, 0, 1, 0, 0. They're a bunch of states. Okay. Great. So now that we've applied the Hadamard, we have this massive expansion, and what we're going to do is measure both. Alice is going to measure both qubits. Okay. Measure both qubits. And let's see what happens here. What's going to happen when we measure both qubits? And we can do this by thinking about what are the states left? What possible states will remain in our state after the psi2 has collapsed? So suppose we measure the password qubit. Suppose we measure the password qubit and we get 0, okay? So all we've done so far is measure the password qubit. What terms will be in the remaining state? What terms will be in the remaining state? And so I could say this is the first term, second term, third term, fourth term, fifth term, sixth term, seventh term, and eighth term. And again, I do very much apologize for the lack of minus signs. But which terms will remain if I measure 0 for the password qubit? Which terms will remain? We measure 0 on the password. That's right. That's right, Emily. So the terms that will remain are the first 2 terms in each line. Because you can see if I measure 0 on the first qubit, these are all 1. Okay, these last 2 terms here are all 1 on the first qubit. So all those terms are going to disappear from the superposition. Okay, we've decided that those terms aren't possible. Okay, now from that, suppose then I measure A. I measure A, which is Alice's Bell qubit, from these 4, 1, 2, 5, and 6. Which further superposition branches are going to disappear? Which further superposition branches are going to disappear? If I measure, what did I say? 1. Let's just say 0. If I measure 0 for Alice's Bell qubit, what are the remaining terms? What are the remaining terms? Right, 0, 0, 0, and 0, 0, 1. And that corresponds to this term here. So the password qubit is 0, and Alice's qubit is 0. The password qubit is 0, and Alice's qubit is 0 still, but Bob's qubit is 1. So there are only 2 possibilities, right? So what I want you to take away from this slide is that for every possible outcome of measuring the password qubit and Alice's qubit, for every possible outcome there are going to be only 2 terms remaining in the superposition. Does that make sense to everyone? For each one of these possible outcomes, and there are 4 possible outcomes, there will only be 2 terms remaining. That makes sense? If we want to do one more, let's think about what if we were to measure 1 on the password qubit and 0 on Alice's qubit. 1 on the password qubit and 0 on Alice's qubit. Which terms would remain? Yeah, 1, 0, 1 and 1, 0, 0. And that corresponds to this term here. Okay. 1, 0, 0, and 1, 0, 1. Where's 1, 0, 1? Here. Here's where we're going. Okay. So with each possible measurement, the state is going to collapse to just 2. So let's take a look at all of these outcomes lined up together. Here's our circuit again. We've measured. Here's what happens. Okay. So if we had 0, 0, we measured 0 and 0. Just as we said before, we get the state alpha 0, 0, 0 plus beta 0, 0, 1. Okay. If we were to measure 0, 1, we get 0, 1, 1 plus 0, 1, 0, and so on and so forth. And now the negative signs are back. And we can see what happens, right? So assume that in those previous equations, and I do apologize again, that those negative signs were correctly placed. You can believe that based on where the negative signs were supposed to be, this is what the state's going to look like. Okay, this is what the state's going to look like. Does this make sense? So, but what's really interesting about this is once we've measured the password qubit and Alice's qubit, Bob's qubit is in the state, alpha 0 plus beta 1. Alpha 0 plus beta 1. And what's cool about that is that was the whole goal all along. The whole goal was to get the state alpha 0 plus beta 1 onto Bob's qubit, and we've done that here. Okay? If the measurement was 0, 0. If the measurement was 0, 1, for instance, we've got a slightly different state, alpha 1 plus beta 0, okay? And so for these other 3 possibilities, we don't quite have the state replicated on Bob's qubit. But before we go to talk about how we can fix these, and we will be able to fix it, it won't require much doing at all. Before we can fix these states, to make sure that we do recover alpha 0 plus beta 1, is it clear how this happened? All right, let's go back to the image. When we measured, we affected Bob's qubit. we measured, we affected Bob's qubit, so that now the state has collapsed to just two superpositions, and the alpha and the beta are now part of Bob's qubit state. Okay. And so we can pretty much just throw out, just kind of like we did in Deutsch's algorithm at some point, we can ignore the password qubit and Alice's qubit at this point and just talk about the state of Bob's qubit, because they've served their purpose. Once we've measured them, we know what their state is, and we don't really need to talk about them anymore. So we can rewrite our system as just Bob. We're just going to talk about the state of Bob's qubit because we know what these other qubit states are, and we don't need to worry about them anymore. Okay. And so how can we affect these outcomes, alpha 1 plus beta 0, alpha 0 minus beta 1, alpha 1 minus beta 0? How can we affect these outcomes so that we end up with the correct state each time? Well, it's really easy. We know what to do because we know what it's going to be like in the case that we measured certain values. Okay. So what we're going to do is just modify our state. Alice is going to send, in step 4, the results of her measurements to Bob. Okay, so let's just say Alice measured 1, 0. She's going to send those measurements, and Bob's going to be like, okay, if Alice sends me the measurement 1, 0, I know that I have the state currently alpha 0 alpha 0 minus. Man, I'm really missing these minuses. Alpha 0 minus beta 1. So what I need to do is apply the Z gate. And if I have 0, 1, for instance, what I would need to do is apply the X gate. So what I thought we would do is just take a look at how the Z and X gate fix each one of these issues so that we end up every time with alpha 0 plus beta 1. Well, actually, let me start. Does everyone see how that would work? How the Z gate would fix this state? We haven't talked much about the Z gate at all. So okay. Yeah, okay. So let's go through that. I'm going to switch over to the Jamboard. Switch over to the Jamboard. So let's go to a new page. And in the case, again, that Alice measured 0, 0, Bob's qubit was 0 plus 1. Nope, that's wrong. Bob's qubit was alpha 0 plus beta 1. But in the case that Alice measured 0, 1, the state of Bob's qubit was alpha 1 plus beta 0. Close, right? So in this case, what we're going to do is apply the X gate. Does everyone see how that would work? Everyone see how that would work? Yeah, so the X gate applied to the 1 state. The X gate applied to the 1 state is alpha 0. And the X gate applied to the 0 state is 1. And so we just recover the state that we were looking for all along. Check, that works. So all Bob needs to do to get the correct state in the end is apply an X gate to what he has. That makes sense? Okay. So now the other possibilities, we had alpha 0 minus beta 1, alpha 0 minus beta 1. And what the Z gate does, this is the Z gate. On generic state alpha and beta, that does is we're going to apply the first inner product, and we're going to apply the second inner product. What you end up with is alpha and negative beta. You guys see where we're going with this now? So the Z gate effectively changes the phase of the 1 superposition from -1 to 1, and from 1 to -1. So what ends up going to happen, Z on the 0 state, it's just going to be alpha 0 again. And on the 1 state, it's going to turn 1 to -1. So we're going to end up with +1. You see how that works? Essentially what the Z does is flip the negative sign, which is exactly what we're going for. Should I go through that one more time? All right. Well, we've got our correct state. Yeah, so we'll get to that in a second. But effectively, if you wanted to do 2 qubits at once, you would need another bell. You would need another bell pair. So let's finish up our little chart here. If we had 1, 1, then we would need to apply the X and the Z gate, because we have alpha 1 minus beta 0. And what the Z is going to do is fix the negative sign, and the X is going to fix the ordering here. Okay, so we end up with alpha 0 plus beta 1. And there we have it. That is the scheme for quantum teleportation. So that's it. So what Bob has to do, let's just review the circuit one more time. So we entangle the password qubit with Alice's bell qubit. Then we apply the Hadamard to achieve those 8 superposition branches. Then Alice is going to measure her 2 qubits. And then we know that Bob's qubit is going to be in one of 4 states that's very similar, if not exactly, this original state. And depending on whether the result of this first qubit is 1, we're going to apply a Z gate, and depending on whether the result of this second qubit here is 1, we're going to apply an X gate. So this combination of X and Z gates just serve to sort of fix the state so that we end up with the correct state in the end. Okay. And that's quantum teleportation in a nutshell. So the key, can we communicate faster than light speed? No, we can't. Could Bob measure the state as soon as Alice does her measurements? Sure, Bob could do that. But Bob would have no way of knowing, whether he had operated on the right state, because he may have needed to apply some X and Z gates as well. And so the only resolution to this problem is that Alice has to send the classical measurements along to Bob for Bob to be able to extract any useful information. And so therefore, we haven't broken the rule that information can travel no faster than the speed of light. And that's it. So to recap, this quantum teleportation protocol has some arbitrary state and we want to send it along. What we need as a resource, we need this Bell state. We need a Bell pair of qubits, and one has to be sent to the sender and one has to be sent to the receiver. And we have two subcircuits. One, Alice is going to apply this C0 and Hadamard and then measure, and then Bob may or may not need to do something on his end as well. Okay. All right, so questions. And what Peter Rohde showed, I'll say one more thing. What Peter Rohde showed was if we could generate a bunch of these entangled qubits, say we have A and B, and we send B here and A here, and then we have another branch where we could have A and B and send A here and B here, and then we had another branch, what we could do is send the state psi to this branch, which in turn would send it to this branch, which in turn would send it to this branch. And then all these branches we've done by creating these entangled pairs, we can send quantum information all over the world, up into space, etc. And right now, I think we're up to maybe 50 kilometers, I think is the furthest we've been able to entangle two photons. I have no idea exactly where we are there, but that's just a guess. Okay, so questions. Yeah, so what if we wanted to teleport two qubits at once? Well, what we could do is we could just create another set of entangled pair, and we could just apply the same operation twice. All right then, if there aren't any further questions, then we will take a short break, 10 minutes, and then Kanav will come back and talk to you about some of, oh, another question, okay. So 3n qubits for sending in, yes. Yeah, the currency in this whole operation is the two entangled qubits, That's the key to the whole, to making this all work. And what Peter Rohde said was the idea of cost, it's going to be the cost of creating these separated in space qubits that are entangled with each other. That's the hard part. After you've separated these, you've created these entangled qubits, the rest is pretty easy. The hard part is getting all these entangled bits together. So sending 5 entangled qubits, that would mean for each single qubit state you want to send along, you would need 2 entangled qubits. You would need a Bell pair, right? So you could think of it as 1 Bell pair every time you want to send something. 1 Bell pair every time you want to send something. So if we have 5 entangled qubits, yes, sending qubits that are entangled with each other, maybe Kanav can jump in and answer that question. How does the protocol extend to sending qubits that are already entangled states?
It works in exactly the same way. So if you have, say, 5 entangled qubits and you want to teleport them, you would do exactly the same protocol, right? Repeated 5 times in parallel using 5 Bell pairs. And you can show that what you get at the end is exactly, after the correction, right? Depending on the measurement outcomes, what you get is exactly the state that you start with of the 5 entangled qubits.
Yeah, to slightly add to that, in the long term, when we have the technologies perfected, if we are like very far apart, then what the two parties would do, what Bob and Alice would do, they would create millions of entangled qubits and keep them with them. So that will be their currency. So like while Alice is leaving for a mission, she would just take millions and millions of qubit with her that she could use for communicating or sending qubits across.